Episode 9, titled Subnetting for Architects, CIDR, VLSM, and Right-Sizing Networks, subnetting is treated as capacity planning rather than a math performance event. The exam may show subnetting in the form of prefixes and address blocks, but the real skill is choosing a network size that matches purpose, zone boundaries, and realistic growth. When you approach subnetting as architecture, you are asking how many endpoints will exist, how many will change, and how much isolation you want when something goes wrong. That approach also keeps you from building networks that are either wastefully huge or dangerously tight, both of which create operational pain later. The goal is to make subnet decisions feel like a design choice you can justify, not a calculation you fear. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Classless interdomain routing, often shortened to CIDR, is the notation and idea that makes modern subnetting straightforward because prefix length directly controls network size. A CIDR prefix is the number of leading bits that identify the network portion of an Internet Protocol version 4 address, and that prefix determines how many addresses remain for hosts. When you hear a prefix length, you can think of it as a capacity knob that trades network count for host count, and that trade is exactly what architects manage. Larger prefixes, meaning more bits in the network portion, produce smaller subnets with fewer host addresses, while smaller prefixes produce larger subnets. The exam often expects you to recognize this relationship quickly, even if you are not doing precise arithmetic in your head. Variable length subnet mask, often shortened to VLSM, is the practical technique that lets you allocate different subnet sizes to different zones cleanly, instead of forcing every segment to be the same size. In older fixed-size approaches, you might carve a large network into equal parts, even when one zone needs far fewer addresses than another, which creates waste or forces awkward workarounds. VLSM lets you give a larger subnet to a production application zone and a smaller subnet to a management zone without breaking the overall address plan, as long as the ranges are non-overlapping and aligned. This method fits modern environments because real networks rarely have uniform needs, and environments like production, test, and management typically scale at different rates. Architecturally, VLSM is about matching address space to purpose, which reduces waste while preserving clarity. Estimating host counts is where subnetting becomes architecture, and the most practical method is to include growth buffers and remember that some addresses are reserved and not usable for hosts. Your initial estimate should account for what exists today and what is planned soon, but also for variability, such as bursts, replacement cycles, and temporary deployments that appear during upgrades. You also want a buffer because readdressing later is expensive in time, risk, and coordination, especially when multiple sites or peering relationships are involved. Reserved addresses matter because the full address count in a subnet is not equal to the usable host count, and practical planning uses a conservative mindset rather than an optimistic one. The key is not perfect precision. It is choosing a size that remains comfortable under realistic growth and avoids frequent redesign. Right-sizing is the discipline of reducing waste without risking fast exhaustion later, and it sits between two common failure modes that show up repeatedly on the exam and in real life. Oversizing creates sprawling broadcast domains, wide trust ranges, and confusing logs where too many unrelated systems share the same segment identity. Undersizing creates constant pressure, forces emergency expansions, and encourages unsafe shortcuts like squeezing new systems into the wrong zone or reusing addresses in ways that cause conflict. Right sizing means you deliberately choose a subnet size that fits the zone's purpose and expected growth, and you revisit that plan when the environment changes rather than letting entropy win. A good right-sized design also supports troubleshooting because boundaries remain meaningful, and meaningful boundaries are how you narrow blast radius and find root causes faster. Heuristics help you move quickly without doing heavy math, and a few common sizes show up so often that you should recognize their feel in terms of capacity. A prefix, commonly spoken as /24, is widely used because it offers a familiar-sized subnet that works well for many general-purpose segments and keeps patterns consistent across sites. A prefix, commonly spoken as /26, is smaller and is often used for tighter zones where you want limited membership, such as management segments or small service tiers, while still leaving room for growth. The exact host counts are less important in this moment than the idea that each step toward a larger prefix reduces capacity, which can be a feature when you are trying to limit blast radius. The exam often rewards the candidate who chooses a reasonable size for a zone's purpose, not the one who can calculate a maximum host number under stress. Subnetting also affects routing tables, security groups, and logs, which is why it matters to architects even when the immediate question seems focused on addressing. Larger numbers of smaller subnets can increase routing table entries and policy objects, which can be good for isolation, but can also increase management overhead if the design is not organized. Fewer, larger subnets can simplify routing and reduce the number of policy objects, but it can make segmentation coarse and increase the impact of misconfiguration. Logs often include source and destination Internet Protocol information, so subnets that map cleanly to zones make logs more meaningful because you can infer purpose and trust level at a glance. When subnets are inconsistent or arbitrary, you lose that signal and troubleshooting becomes slower, which is a hidden cost that scenario questions sometimes hint at through operational strain. The best designs balance routing simplicity, policy clarity, and log usefulness, and subnetting is one of the levers that shapes all three. To make subnetting audio-friendly, it helps to walk through one example where you split a single network into 3 segments based on zone purpose and capacity needs, without turning it into a spreadsheet exercise. Imagine you start with a reasonably sized private network block allocated to a site, and you need to carve it into a production segment, a test segment, and a management segment. Production needs the most room because it will host user-facing workloads that scale. Test needs moderate room because it will grow but should not be unconstrained. And management needs the least room because only a small number of administrative systems should live there. Using VLSM, you allocate the largest subnet to production first so its boundary is clear, then allocate a smaller subnet to test, and finally allocate the smallest subnet to management, ensuring none of the address ranges overlap. The architectural point is that the sizes reflect purpose and growth rate, and the order of allocation reduces the chance of painting yourself into a corner later. Pitfalls in subnetting are often more operational than mathematical, and 2 recurring ones are overlapping subnets and mismatched gateways. Overlapping subnets create ambiguous routing, break peering, and virtual private network connectivity, and produce failures that feel random because traffic can be sent to the wrong destination silently. Mismatched gateways occur when the default gateway configured for a host or segment does not match the subnet design, which can lead to one-way connectivity, intermittent reachability, or confusing behavior where local traffic works but routed traffic fails. These issues are common in rushed changes, mergers, and multi-site growth when address plans are copied without reconciliation. The exam often provides subtle clues like after a new site was connected, or after a range was reused, and those clues should trigger suspicion about overlap and gateway alignment. A disciplined subnet plan reduces these risks, and disciplined change control prevents them from returning. VLSM becomes especially useful when you need to match different environments, like production, test, and management, to their actual needs rather than giving them equal space out of habit. Production often has more endpoints, more scaling events, and more service dependencies, so it typically deserves a larger subnet or a design that supports expansion without readdressing. Test often needs enough space to be realistic, but should remain bounded so it does not accidentally become a shadow production environment that consumes resources without governance. Management should be intentionally small and tightly controlled, because fewer systems should have administrative access paths, and because strong boundaries make auditing and containment easier. When these environments share an address plan, VLSM allows you to keep them logically separate while still being part of a coherent site-wide or organization-wide design. This separation supports security and operations because it reduces the chance that mistakes in test affect production and limits the reach of management systems by design. A memory anchor that helps many learners is connecting prefix length to the feel of address count, so you can make reasonable decisions quickly even when you are not calculating exact host counts. The feel is that as the prefix length increases by 1, the subnet capacity roughly halves, which is a mental lever you can use to reason about size changes without a calculator. If a zone is too large and you want to reduce blast radius, moving to a larger prefix, meaning a smaller subnet, is a natural direction to consider. If a zone is running out of space, moving to a smaller prefix, meaning a larger subnet, increases capacity but can also increase exposure if you are not careful with segmentation controls. This anchor also helps you interpret answer choices that propose resizing, because you can sense whether the proposed prefix change is a modest adjustment or a dramatic one. The exam tends to favor candidates who recognize these scale effects and choose changes that match the scenario's urgency and constraints. For a review prompt, practice stating the steps you would take to right-size a subnet without calculating exact host counts, because architecture is often about process and justification. Start by naming the zone and its purpose, then estimate the number of endpoints it needs today and the realistic growth it will see over the planning horizon. Add a buffer and remember reserved addresses. Then select a prefix whose capacity feels comfortably above the expected need while still supporting segmentation goals. Confirm that the chosen subnet fits into the larger address plan without overlap, and confirm that routing and policy boundaries remain clear and manageable. When you can state this process smoothly, you will be faster at recognizing which answer choice reflects disciplined planning and which one is just guessing. To close the core with a practice prompt, imagine a zone that is expected to grow rapidly and size subnets in a way that supports that growth without turning the environment into one flat, overly permissive segment. Rapid growth suggests you should allocate more capacity than today's footprint would imply, but you should still keep zone boundaries meaningful so security and operations do not degrade as the environment scales. A practical approach is to allocate a larger subnet for the growing zone while ensuring that sensitive or administrative systems remain in smaller, controlled subnets that do not expand simply because production expands. You also want to leave adjacent address space available so expansion does not require readdressing into disjoint fragments, which complicates routing and policy. This exercise reinforces that growth planning is not simply make everything bigger, it is make the right parts bigger while preserving boundaries and clarity. That is an architectural mindset, and it maps well to how scenario questions are written. In the conclusion of Episode 9, titled Subnetting for Architects, CIDR, VLSM, and Right-Sizing Networks, the takeaway is that subnetting is capacity planning guided by purpose, growth, and control, not a contest to see who can do binary arithmetic the fastest. CIDR gives you a prefix length that directly controls network size, and VLSM lets you allocate different sizes to different zones so your address space matches reality. You estimate hosts with buffers and reserved address awareness, right size to reduce waste without triggering early exhaustion, and keep a few common prefix fields in mind, such as /24 for general segments and /26 for tighter zones. You consider routing tables, security groups, and log clarity as part of the subnet decision, and you avoid pitfalls like overlap and gateway mismatches that break connectivity in subtle ways. Recap the heuristics by remembering that prefixes change capacity in predictable steps. Then assign yourself one right-sizing rehearsal by choosing 2 zones, estimating growth, and selecting prefix lengths that preserve both capacity and blast radius control. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.